Okay, cool. So are you all on the notebook?
Are you also starting a meeting?
Yeah.
Where's the notebook?
It's the computer vision channel. I don't see you there, so let me add you. What's your name?
Adam Romero.
Right now. Okay, everyone else got it, right? Okay. So yeah, we first want to go over the section. Well, if you want to run the notebook in parallel, you'll have to create a copy in your own Google Drive and run that from there. But the outputs are already there for now, so we can just go through the notebook. So I would like first to briefly go over the context, as I put it here in the section. And we'll first go to the feed-forward neural network. So from what you taught me in the PyTorch tutorial, you guys are not too much familiar with actual neural network architectures. So the most basic one is the feed-forward neural net, where we stack layers on top of each other from our input layer, where we actually have the input values, to the output layer, where we get our predictions or get whatever we want to get out of the neural network. And how each layer works is that each layer has what we call nodes, which is a hyperparameter. You have to select how many nodes you want within each hidden layer and how many hidden layers you want. The input and the output layer are fixed depending on like the application. And how it works is each node in each hidden layer takes as input all the outputs of the previous layer, computes essentially a weighted like combination of them, perhaps adds a constant, which we call bias, and then passes that through a non-linear function and computes its output. And if you do that for the whole layer, then again, you have the outputs for the entire layer, and you move to the next and the next layer until you go to your output. So that's kind of pretty much the gist of feed-forward neural nets. And in below the diagram, I also have a cell where I've created a linear neural network, like we did in the PyTorch tutorial. So again, we wrap it around NN sequential because we are just passing our inputs through existing modules. So for example, here you see I have the feed-forward neural net, which assumes you have 1,000-dimensional inputs, and then creates a hidden layer with 500 nodes. After that first hidden layer, we apply the ReLU to the outputs, which is our non-linearity. And then from that, we have another hidden layer with 100 nodes. So that's what the linear 500 to 100 denotes. Then I use a different activation function, then another linear layer that takes you to 50 nodes. Then I apply a sigmoid, a different activation function. And then finally, we go from the final hidden layer, which has 50 nodes, to our output, which has 10 nodes here. And again, for our inputs, we have to always have them in a batch. So we have the 1,000-dimensional vectors, but we need to have multiple of those in our input tensor for it to work. And if you see, indeed, we pass our input through the feed-forward neural net, and the output has the same batch size. So the first dimension is identical, but the output is the same dimension as the final layer, which is our output layer. So moving on from feed-forward neural nets to convolutional neural nets. So we showed you convolutions in the last workshop and how they work. And here I have an animation of what a convolution is actually computing. So you can see this kind of convolution kernel, as we call it, moving through the image and computing basically a pointwise. You first do the pointwise multiplication of the elements of the kernel and the corresponding like shadowed region of the image, or whatever inputs you have, and then you add them up together and you get the output. So you can kind of see in this, the first one we have a 2D convolution. In the second GIF, I have a 1D convolution, which is exactly equivalent. But you'll see that the difference is that for the 2D kernel, you can actually notice that it skips essentially 2 pixels every time it moves around, whereas for the 1D convolutional kernel, it moves around in steps of 1, so it goes through the entire thing. We can use what we call strides, so you can set stride to be equal to 2 to essentially downsample your images or whatever input you have. So images may be very high dimensional and you want to decrease the dimension of your data to make the network more efficient. So let's go to the first code cell where I'm creating, again, using the sequential module. I'm creating a very simple 2D neural net. So there is a lot of information here to digest, but let's look at it one step at a time. So the first module that I'm creating in the sequential is a conv2D. So that's a convolutional neural network layer for 2D inputs. And what we mean by 2D is essentially that your input is going to have essentially 4 dimensions. The first dimension is going to be the batch size, always. The second dimension is going to be the number of channels. So you should think the number of channels as the different features that exist in 1 pixel. So you have the 2D structure of the image, and at each pixel you have not a 1-dimensional feature, but like you have a vector of features. In your input, if you are dealing with actual images, your vector is going to have a dimension of 3, and it's going to be RGB, the different colors of the image. But as we move through the network, we can manipulate what the length of the feature is going to be. So that's what you're doing by the channels, the channel hyperparameters. So you can see that in channels equals 3 denotes that I'm expecting a 3-dimensional vector per pixel in the input. And out channels, that's going to give you 64-dimensional vector for each pixel. So we have, again, batch size, we have the number of channels, and then we have width and height, or height and width. I can never remember which one is first.
It's width.
Width and height, okay. Then the third important argument in a convolutional network is the kernel size. So it's essentially the thingy that moves around your input and computes like this multiplication pointwise and then the summation. So you're denoting that the kernel is going to have 4-pixel width and 5-pixel height. And then the stride is, as I explained to you earlier, what's the step that the kernel is taking in the image while it's moving around. So when you have just an integer there, it's going to have a step of 2, both for when it's traversing in one direction and the other. So it's going to be equivalent to exactly the GIF, the first one, which you can see when it's moving to the right, it takes a 2-pixel step, but also when it moves towards the bottom, it also takes 2 steps. Then again, after that, we apply again nonlinearity. We go to the second layer in our neural network, which has to expect 64-dimensional channels, because that's what we created in our output in the previous one. And then we arbitrarily just double it again. And you can see kernel size now, it's an integer instead of a tuple. So it's going to create a 4x4 kernel there. Again, a nonlinearity. And then we have what we call pooling. So pooling is essentially an operation that's parameter free. So our convolutional kernels obviously have parameters, which are the elements which we multiply the images with. The average pooling is essentially parameter free. And what it does is essentially like a kernel, it goes over the image and it performs some simple pooling operation. For example, here you can see that it does averaging, so adaptive average pool 2D. And the kernel here is 1, because what I'm trying to do is, well, I don't know if the argument exactly is named kernel, but what we're trying to do here is we have a very high dimensional image at the output. Like we have the batch size, we have the out channels of the previous convolutional kernel, so 128, and then we have whatever width and height has resulted from our input image. And what the average pooling does is it goes through the entire image and it averages the feature vectors. So you go from a, say, if the batch size is 16, you go from a 16, 128 width and height to 16, 128, that's it. So the reason you do this is because at some point you want to have like our normal feature vectors instead of having these very high dimensional objects, so that you can use linear layers to project them to, for example, predictions. So once we have this 128 dimensional feature vector for each image, essentially, so because we went from batch size channels width height to batch size feature size, so each image now is represented by a 1D vector of size 128. So you're going to project that 128 with some linear layer to like 10 classes, for example, if we're dealing with classifying digits in MNIST. And the reason I'm using thereafter NN flatten is because we're not actually getting 16 by 128. We're getting 16 by 128 by 1, 1, I think. So it retains the dimensions. So when you flatten, because the dimensions are unitary, they just disappear. So if you see at our example execution here, I'm creating indeed a random input which has dimensionality batch size 3 and random width and height 224, 224. I'm passing it through the CNN, and you see that the output is indeed 16 by 128. So if you actually wanted to do classification, you could add another module after the flattening, which would be NN linear from 128 to the number of classes you want, for example. And let's go to the next figure just to get a better grasp of what's happening when we're going from example from 3 channels to something that's higher dimensional. In that case, the kernel essentially also has a width. Well, no, the kernel has a width and the height. The kernel also has that other dimension to do the point-wise multiplication with the features that exist per pixel. And that's going to give you only an actual 2D output in your output if you have only one kernel. So if you denote that you want in your output to have 64 channels, you'll create 64 such kernels that are going to be essentially size. Let me see what I defined in my neural net. My first layer was 4 by 5. So the actual kernel size is going to be 3 by 4 by 5 because we have 3 channels. And because I want my output channels to be 64, I'm going to have 64 of those. So it's not like the first GIF that I showed you, which had the 1D, like the 2D structure with the 2D kernel. That's for visualization purposes only. Both of these objects are 3-dimensional, but we consider only the 2-dimensional to be the actual structure of the image. So that's mostly semantics. It doesn't have anything directly to affect you with, but you should know, like here, for example, I'm plotting after the figure that shows what the convolution results in. So you see a cell which plots the shape of the weights of the actual convolutional layer. So where it does CNN brackets 0, it grabs the first module that exists in the CNN which was our convolutional kernel. And if we could do dot weight, then we go to the actual tensor that stores the parameters. And when you do dot shape, you can see that indeed we have weights that are 64 by 3 by 4 by 5. So the 3 by 4 by 5 it's each kernel, and the 64 is like kind of the collation of the kernels. And very briefly, I want to note that what's interesting with CNNs, if you see the next figure, you can take a look at it on your own, I guess, is that CNNs are a strict subset of feed-forward neural nets. And how you go from a feed-forward neural net to a CNN is that you zero out connections that are too distant, and you do also weight sharing. So the weight sharing happens because we move the kernel around the image. So the different parameters are denoted by the different colors in the figure. Are we all? Yeah, we're all, I guess, on the same page. Please check them.
Yeah.
So the different parameters, when it's the same color, that means that the parameter is shared. And you can see that when one node is too far away from other nodes in the previous layer, it's not even connected to that. And that's because the kernel is applied to small regions in the image. So CNNs are a strict subset of feed-forward neural nets. But that's actually the reason why they're kind of more powerful, because we have this inductive bias in the network that we actually want it to model local relationships. And we want it to look for those relationships all over the image. So if we go to the next figure after that, there is an image of a cat. And you can see it would be reasonable for the face of the cat to appear in all places, like in the image. It doesn't have to be in the center, for example. So by moving the convolutional kernel all around the image, if that kernel is looking for the pattern cat head, it's going to find it. Otherwise, if we had like this convolutional kernel only being applied to like the center of the image, then the cat would have to be centered in the image for it to capture those features. So yes, we are creating a strict subset of FFNs, but we're doing so because we have good reasons to believe that that's an actual like useful property for the model to have. And in this manner, because we are zeroing out distant connections and we are sharing the weights, we are reducing the parameters we have to learn. So not only are we sort of inducing useful properties in the network, but we're also reducing the search space of the parameters, which makes it easier to optimize, or you can even create much larger neural networks compared to the ones you would create with feed-forward neural nets, because that in FFNs, FFNNs, the parameter number would explode, but for CNNs, you can like keep it more constrained. So that was it for the CNNs. If you could go then to recurrent neural nets. So recurrent neural nets are essentially kind of a format of how you can utilize neural networks to model sequences. And why we do this, we can have like sequences that have arbitrary length, for example. So you cannot predefine the size of the neural net. So if you see in the GIF, on the left-hand side, we have like this very condensed representation of the network. But when the animation plays, you can see it actually being rolled out. And what's happening is you have an X that has that's an actual sequence. So it's not a 1000 dimensional vector. It's an n by 1000 dimensional vector where n can be variable. And you can see, for example, it says X t minus 2, t minus 1. That's different elements of the sequence. So what you do with RNNs is that you essentially process the sequence in sequence. So you process the first element of the sequence. Then after you do that, with the neural network denoted by H here, you create an output that's Y if you want to do element-wise like classification of a sequence. And then for the next time step, your H is going to take as input the next element in the sequence, but your H is also producing some what we call hidden state, which it passes to itself in the next time step. So the hidden state is supposed to essentially encode what the neural network has seen up to that point in the sequence, so that it knows like how to classify the points that are to come. And that's, for example, opposed to, say X is a video. So H can be a convolutional neural net, but a 2D convolutional neural net that processes one image at a time. You could theoretically just run the CNN on individual images, but you may lose information about the flow of how things are happening in the video if you don't pass some information from the previous time steps to the next ones. But that fact alone makes it very computationally intensive, because if you see the final graph, the final output at your final frame of the video is going to be connected to even the first frame of the video. So it creates a very long computational graph, and it takes a long time to actually run through the sequence because you have to be done with the processing of one frame to go to the next. You can't do them in parallel. But what that allows you to do is have arbitrary length sequences, and that's basically why we use RNNs. So I want to take you directly to transformers next. So we skip to the next section. And yeah, why we skip to the next section is because even if you do try to model sequences, at least for the purposes of this project, I would just say model individual elements and then do some sort of pooling at the output. So you'll have a feature vector for each frame in the video, just average the feature vectors and get one final feature vector for the entire video. It's going to be much more like feasible for us to do the project like that, instead of having the overhead of having to run also the RNN. But I wanted to show it to you anyway. So transformers is like the main buzzword right now in deep learning. And they are kind of used to model everything, but they were first proposed to model language tasks. So the RNNs can also be used for language tasks. You can imagine that X is a sentence, and you're passing in word by word in the RNN to do some classification. For example, figure out what the sentiment in the sentence is. You run through the entire sentence, and then at the final output, you use that to perform some classification task. What the transformers are doing is like a different spin on how you want to do this. And let's first go into how we're actually creating a sequence from a sentence. So you can see in the first figure that you have a sentence called "Let's tokenize, isn't this easy?" And you're actually trying to break it into multiple tokens, as we call them, to create a sequence. And at the bottom, you can see the easiest thing you can do is just break on spaces and consider its like word, that each token that results from that its own word. But we most likely would like to get something akin to the top two rows, where you're using more elaborate rules to break the sentence into individual tokens. And why we do this is because like easy question mark, you can kind of decompose the meaning into easy and question mark, and therefore you wouldn't have to model easy question mark, easy exclamation mark, easy comma, easy this, easy that. You break it from the punctuation, and then you keep the word itself. And therefore you have to model easy once, and then you can combine it with whatever modeling you have for punctuation points. And there are other tricks we can also do. For example, when you have plurals, so for example, dogs, you might want to break dogs into dog and s, and therefore you'll have only like one representation for dogs. And if you want to take it to the plural, you'll combine it with the representation you have for s when it's like singular. When s is singular, the network would have learned that this denotes that I need to make the previous like word in plural, for example, or something like that. So there are ready-made tokenizers for this. It's not something you have to do from scratch. And thereafter, when we break our sentence into individual tokens, if we go to the next figure, what you want to do is take these words and project them to word embeddings, as we call them. So that's going to be a feature vector that corresponds to each of the words. And that's in contrast to what otherwise you could have done by creating an one-hot representation of the word. So is everybody familiar with what one-hot means? No. Below the figure, you'll see, for example, I have this kind of tuple of zeros and only a single one. The dimension that's a one is going to denote what word is that. So if you have 1,000 words, you have to create a 1,000 dimensional vector, and for each word you assign a one in one specific one of the dimensions. However, when the vocabulary grows very large, for example, like when you're actually doing this in a real world setting, you may want a vocabulary that's large enough, and very small vocabularies may consist of even 30,000 tokens. So having a 30,000 dimensional representation is not very convenient. But the representation in the word embeddings, it can be as high or as low dimensional as you want it to be. And moreover, it's not going to be sparse. So you are going to have values that are different from 0 and different from 1 in all these different dimensions. And the interpretation of each of the dimension is left up to the neural network to find out how you assign meaning to each one of the dimensions of the word embeddings. And also, to be honest, we indeed go from like this one-hot representation to the embeddings. There's nothing else you can do. So we are essentially building a lookup table where you have rows as many as you have words, and each row contains the embedding of that specific word. So, you know, at some point you have to indeed go from one-hot representations to word embeddings. You can skip that part, but it's good to know that you need to build these word embeddings or to use existing word embeddings. There are existing word embeddings. People have trained word embeddings on corpora of millions or billions or even trillions of tokens. So there's no need for you to create it from scratch, but still that's something that you'll need to do. Create the words so you can map them to the embeddings. So that was for language. So that's how Transformer, you can encode the sequence of words. But how do you create a sequence from an image? So I said that the Transformer is a universal encoder. So the Transformer can model language, but they also model images. And how they do this is, as you see in the next figure, they break the image into small patches, and then they put them in order, and they create the sequence like that. So very simple stuff. They also do a post-processing step after that, where they project these 2D patches into, again, feature vectors, similar to word embeddings. And how you do this is, for example, you can take this 2D square, you can flatten the values, and then use a linear layer to project it to whatever dimension you want to project it in. So is that understood what I mean by projecting it to a feature vector right now, for example? How you would go about doing this? Okay. So let's go to the architecture of the transformer itself. So on a very high level, you have an encoder and possibly a decoder. So the decoder can be optional. And what the encoder is doing and what transformers are doing, why they have become very popular, is that instead of doing this as RNNs do it, where you would have the sequence of words and you would take the first word, process it, then take the second word, process it, then take the third word, process it. What transformers do instead is they process everything at once. And how they do this is essentially they are set operators. So transformers operate on sets, and kind of each token in your input is a kind of like an element in the set. And for sets, you obviously they don't have any inherent sequence in them, so you process them in parallel. I don't think I should go into too much detail of how this is happening, but I'm gonna show you the main. Let me finish describing here what the encoder and the decoder are doing. So the encoder is taking the entire sequence, and then for each individual token is obviously missing information from the entire other sequence. And so you're looking at when you start in a context-free manner, it's only individual words, because you take the word, you find out which word that is, and you map it to its word embedding. And so what the encoder does, it kind of pulls information from all the other words in the sequence and embeds them in each of its input tokens. So you can think of it, for example, like why that's useful is you have an adjective and a noun, and the noun doesn't know what the adjective is doing before it. So when they go through the encoding of the transformer, the noun is going to see that it has an adjective before it, and it's going to integrate the meaning of the adjective to like its word embedding. So for example, you can have a pretty or an ugly dog. And therefore, when you integrate the meaning of pretty or ugly to the word dog, that's going to alter how like the network perceives the dog thereafter. So you have multiple encoder layers which do that. Each layer does that once essentially. So its encoder for each one of its input tokens looks at all the other tokens and brings in the information that the token needs. And then you repeat that process until like you've basically mined all the information from the entire sequence, and each token has kind of reached its ultimate, say, meaning. So at that point, what you have, because again, the transformer is a set operator, its output is also the entire modified set of elements. So however many tokens you had in the input, the encoder is going to give you at the output all these tokens, but modified by the process which as described. So if you want to do classification, again, if you want to do sentiment analysis only on the sequence, you can grab a single special token from the sequence. So if you're going to do what we call sequence classification, or classifying the entire sequence, you can prepend a special token that is supposed to represent the entire sequence. And then you just grab that token from the output and use that to perform classification. But in this figure, for example, it's trying to do translation. So it actually needs to generate a different sequence that may have like a different number of tokens. So you can see it goes from "Je suis étudiant" to "I am a student," which is the English translation of that French sentence in the input. So in that case, we have the decoder, which essentially takes as input the output of the encoder and starts producing one token at a time. And it does that in an autoregressive manner. So are you guys familiar with what autoregression means? Kind of. Well, what this essentially it's doing is, yes, for input, you take the encoded sequence, and then you produce the first token. Then you take the first token and add it to your input and produce a second token. Take the second token and add it after the first input, third, until it produces the special end of sequence token, which you have added on purpose to the decoder so that you know when to stop producing like tokens. So autoregression is essentially that as you're generating a sequence of outputs, these generated outputs are added into your input step by step. And in the next figure, we're gonna very briefly look at how this pooling of information happens. And it happens through the mechanism which we call attention. So each token in the input attends to all the other tokens in the input to pool the necessary information. And how it does that is we have a word embedding, which is a d-dimensional vector. So from that d-dimensional vector, you compute a query vector. So that query vector is supposed to encode what that specific token is looking for in the sequence. You compute also a key vector, and the key vector is supposed to denote what that token has to offer to the other sequence, to the other tokens in the sequence. And finally, you also compute a value vector, which is supposed to essentially encode what information should be pulled from that token if any other token actually needs it for its meaning. So how you do this is you create this 2D matrix of E's, E, I, j, and what E is supposed to denote in that figure there is like how much Q0 wants to attend X0. E0, 1 denotes how much Q1 wants to attend to X0. So Q1, remember, is the query for token T1, and X0 is the key for token T0. So E0, 1 tells you how much attention must T1 pay to the contents of T0. So you create this square matrix where essentially here, I think in each column, you have how much attention should the first token in the sequence pay to all the other tokens in the sequence, including itself. Second column, how much attention should the second token in the sequence pay to all the other tokens in the sequence. And you kind of normalize this so that each column sums up to 1 and has non-negative elements. So it's essentially a distribution, probability distribution. And then you take the values. So remember, that's kind of the information that should be pulled into the other tokens. And you compute this convex combination of the values. So you know how much each token wants to attend to all the other tokens. And therefore, you multiply the attention that each token wants to pay, wants to attend each other token by the value of that other token. I don't know if, I hope this is making sense. I may be making it more complex than it should be. Is it making sense? At least conceptually? Okay. And therefore, at the output for each token, you get a weighted sum of the value that every token has to offer. And that value is, the dimension is equal to the dimension of the value vectors that you compute for each token. But if you make sure that that dimension is equal to the dimension of the original token, in the output, you're going to get an enriched sequence that has the same dimension as the input. So that's usually what we do. We don't like modify the dimension internally, or the hidden dimension as it's called. We don't modify it. We make sure that it remains the same. And then I'm linking to some like tutorials or blogs which you can look at to better understand transformers and attention. I think if you take away anything is that at least learn what these things do conceptually, maybe not at the actual implementation level, but know the high level stuff, so you know where you can apply everything. And finally, I also have a couple of links at the end that speak to all the the networks that we showed you today, but it also, that's the final section called resources to Scheme, that's separate from the networks, but it contains information about all the networks, and it contains information about optimization, this and that. They are basically intros to machine learning, or to deep learning rather. So if you go through the entire thing carefully, then you'll have a good understanding of how neural networks work. So What else we have prepared for you are utilities which you can leverage to create your projects. So if you go to using state-of-the-art models to build your own projects, there, what I'm doing is I'm taking transformers and very deep convolutional neural nets that other people have trained, and therefore their outputs are not random. They have some meaning in them that discriminate, for example, cats from dogs. And you can use these embeddings to perform some tasks. If you want to expand beyond those tasks, you'll need to modify some of the utilities provided, but it should be good practice for you to become to familiarize yourselves with these state-of-the-art architectures and how they're implemented. So first, in the libraries, I'm just doing my imports, but let's go over them so you know where everything is coming from. So first of all, if you are running a Colab notebook and you include, I think any notebook, right? And you include the exclamation point.
Yeah.
Then it's gonna essentially run a command line argument as if you were using your bus terminal or whatever. So here I'm using my pip to install this library called transformers. And the transformers library has implementations for many kinds of different transformer architectures. And you can also load pre-trained weights from them. This is provided by the company called Hugging Face, and everything is open source. You can find implementation on GitHub, and you can find the weights. They have some server which you have access to where you can download the weights, or you can use functions that they use where it downloads and loads the weights to your models automatically. So you don't have to manually download something, store it in some folder in your system, and then load it yourself. So we'll see how we do that. And in the second cell, you can see I'm also using Torch Vision. We saw Torch Vision for transforms, so I'm also importing transforms here. But you can also access models from Torch Vision, where you can torchvision.models, and I'm only using for now ResNet. ResNet is an architecture that I think in 2015, I think was the first one that surpassed human performance on the large image corpus called image dataset called ImageNet. And the reason it did that is it had kind of some property in its architecture that allowed for the gradients from the output to be propagated without too much loss to the earlier layers. So that's a gradient descent and optimization detail, but maybe it's worth looking up to get a sense of what tricks people employ to make the networks, larger networks, trainable. And finally, I'm actually importing from the transformers library, and I'm importing auto classes. So what these auto classes do is that you guys can specify what model you want to load, and the transformers library is going to figure out which architecture fits the model that you provide, and what you provide is essentially a string that points to the model you want to use. And we can actually, if you Google Hugging Face space models, when I say space, I mean the character space, probably the first link that's going to come up is actually the repository of models that they have. So is everybody at the web page? We should be looking at something like this. Google Hugging Face models, and the first link should point you to the repository.
Could you share the link in this?
Sure.
Thank you.
So there you'll see two things. First of all, what becomes apparent immediately is on the right side, you have what they call model cards. So these cards should ideally describe what the model is, what it was trained on, what the model is supposed to do. And how you load them in your code is that you do automodel dot from underscore pre-trained, and then you just pass this exact string you see in the web page, and it automatically loads the model for you. So for example, the first one that comes up, and that's because it's the most widely used, is the BERT dash-based dash uncased. That's from that's a model called BERT. If you've heard, I'm assuming you have, right? Well, we can speak a little bit about the first two models. So the first model is a BERT-based model, so a BERT model, and the second model is a GPT model. So you know GPT, I hope. That GPT-2 is an earlier version that doesn't work quite as well as the current ones do, and therefore it was open sourced. The ones that work well are held behind closed doors. So what BERT is doing, BERT is what we were saying earlier, is just an encoder. So however many tokens you put in the input, that's what you're gonna get in the output, but they're gonna be processed. And it made a big splash in 2019 because it was kind of the first very large transformer that was trained on general language that was released. And how they did that was we have like the text that's available on the internet. It doesn't have any labels for some specific task. It doesn't tell you what sentiments the sentence is expressing, but you do have the actual sentences, you have the structure. So what they did is they went and they randomly removed words from the input and replaced them with the special token mask. So they created a special token which they called like square bracket mask square bracket. And what BERT had to do was at the output, go and for every masked token, predict what's the word that's missing from there. So that's a task you can devise yourself. You don't need any labels. You have the sentence, you remove the word, you hide it from BERT, but you know what it is. So at the output, you want BERT to predict what that word is. And what it's essentially doing is you have created your vocabulary, as we were saying earlier. So you know which word from the vocabulary is the one that's missing from the sentence, and you perform a classification task where you need to select which word from the vocabulary is missing there. So they did that with a lot of data and a lot of GPUs. And when they did that, they released the pre-trained parameters. So people could just grab this model that Google had pre-trained on like 92 GPUs for like 3 months or whatever, and just tweak it a little bit on a smaller amount of resources, and could use it to do any kind of task. You can do, again, sentiment analysis. You would grab the pre-trained BERT. You would have, say, 6,000 examples, 6,000 examples of sentence and sentiment expressed. You would train BERT on only these 6,000 examples, and BERT would be able to perform like sentiment classification at a level which previous models wouldn't be able to. And GPT, what GPT is doing is an encoder-decoder architecture. So the modeling task they chose to train GPT, again, with no labels, is given the previous tokens in the sequence, what's the next token? So it's what you may have called, where people say, oh, these transformers are only doing next word prediction. That's what they mean. That's actually the task that the GPT models have been pre-trained to do. So you have text from the internet and you give it part of the text and you have it generate the remaining tokens. And obviously you have hidden them from the network, so you know which ones they are and you can use them to supervise. So these are kind of two different approaches that people use to pre-train these transformer models. And when they open source them, when they release the weights, we are able to use them and tweak them to our task to get better performance than we would compared to, say, like using a transformer, but initializing it from scratch. So the weights would be initialized randomly. Instead, you initialize them from these pre-trained weights, which have good natural language understanding, as we kind of call it. Now, whether it's actual understanding or not, that's up for debate, but whatever. So in the next cell, you shouldn't be like what I call implementation of ResNet for feature extraction. Don't pay too much attention to it, but what I'm essentially doing here is I am loading the pre-trained weights for ResNet. And ResNet is also like a PyTorch module. So I know what modules it contains internally. So I just dispose of the final layers that perform the classification, and I'm only keeping the layers that give me features instead. So when you call the ResNet embeddings class, well, when you initialize it, when you try to call it, it's going to give you back embeddings. It's not going to give you back predictions as it would have otherwise. And depending on which one of the ResNets you use, because they trained multiple, you'll either get 512 dimensional representations or 2048 dimensional representations. And we'll see how you can choose different ResNets, but I guess it's not too difficult to describe. So because ResNet was the first architecture, as I was saying earlier, to deploy this trick to be able to make the networks more deeper, they named the networks that they released out of the number of layers that they have. So the different alternatives you have is ResNet 18, ResNet 34, ResNet 50, ResNet 101, and ResNet 152. So the biggest ResNet has 152 layers. So let's go to the general purpose image dataset with optional text. So you guys are obviously free to do any task that only contains images, but because people are increasingly using text with images as well, I've like implemented this general utility for you to be able to load your dataset into like a single dataset class, whatever it is. So for your dataset class, again, as we said in the PyTorch tutorial, you need to inherit from the dataset class that you import from PyTorch. And you only need to essentially define the initialization method, the len method, and the getItem method. So if you quickly scroll through the class, you'll see that these methods are implemented. So init, len, and getItem. Remember that for init, you can have whatever parameters you want. For len, you have no parameters. And for getItem, you just have one parameter, which is the index. And let me also remind you that when you define getItem, how you access it is through the square brackets. So if you do square brackets 0, it's essentially going to call getItem 0. And I am also defining a collate function. So the collate function is gonna essentially it defines how you go from one single input to a batch of inputs. So as we said, we always have to have batches, but for the dataset class, you only define how you grab one element from the class. So when we, again, pass it to the data loader, as we showed in the PyTorch tutorial to do the actual training, the data loader needs to know how to go from individual examples to batches of examples. So I'm integrating this function here. You could have defined it otherwise outside of the class, but I like to define it within the class because it's kind of, it's contained in the class that's going to use it. So I guess we'll see what the dataset class can do in practice. So let's not go over the implementation. I've tried to include comments. I hope it's readable for you guys. If not, you can always reach out to us. So let's go to the second function that's there. And that's used essentially to split your data set into train, development, and test sets. So if you guys haven't encountered this, have you guys encountered these concepts before? Okay, so when you're developing your project, you are going to actually train your model on the train set, perform evaluations on the development set, and say for the final presentation and only for the final presentation, then you're going to use the test set to get the final metrics. That's how you're supposed to use it anyway. People don't actually use it like that, but whatever. And yeah, the inputs to the split dataset class are simply the length of the size of the dataset and the ratios of the different like splits. So by default, the splits are 80%, 10%, 10%. So you'll see that in the tuple in the input, I'm just defining two of those. That's because the third one is defined uniquely by the other two because they have to add up to 1. So yes. So that's with the data set. Let's briefly go over the actual models that are going to do the feature extraction for you guys. And first, I'm defining this function called Hugging Face image extractor. So Hugging Face, we were talking about language models before, but Hugging Face also has implementations for transformers that process images, as we saw with the image patches. So I have created a function here that takes in as an input the model you want to load. So again, you go to Hugging Face models, you look for the vision model you want to load, and you just copy paste the string and it's going to load it for you. And the other thing is the device. Again, if you have access to a GPU, and we're trying to give you access to a GPU, but even if we don't manage to get some pro accounts anywhere, you can still use GPUs in Google Colab, but you'll have some time caps for how long you can use it. For example, when I was using it, I think it was around 12 hours.
It's 12 hours, or there's a memory limit for GPU of Colab. So if you like cross that memory limit, then it will like disable you for the next until the next day. So it refreshes every 24 hours.
Yeah, you need to be careful with the memory, obviously, and we're going to talk about that. But you should probably use a GPU. So if you remember from the PyTorch tutorial, what the device object is, or what the format of the device parameter is a string where you either say CPU or you say CUDA : and then the index of the GPU. If you're using Colab, you're just gonna have one GPU, so the index is gonna be 0. It's 0 index. For my server, for the server in our lab, for example, where we have 4, I can say CUDA : 0, CUDA : 2, CUDA : 3, whatever. And the other thing I should note is that these functions that we're going to see right now, they're going to go from the original images. So you're going to have 3 by height by width. It's going to take you to just a 1D vector. Depending on what model you use, it's going to have a different dimensionality, but it's going to significantly reduce like the dimensionality of your inputs. So they are easy to work with, and they have some predefined kind of logic to them based on the training of the neural network. However, because you're not training, you don't have to train these large models to fine-tune them. You could run this on the CPU. It's going to take a while. Extract the features, store the feature somewhere so you don't have to rerun the feature extraction, and then build whatever you want to build on top of the features. So the features are going to be your regular, like your data set is going to be n, which is the number of samples you have, by say 1028. And then you can use sklearn to like use SVMs. You can do logistic or linear regression on them. So what these functions are designed to do is go from this high dimensional input, which you can't work with directly, to very much lower dimensional inputs, which you can like leverage from sklearn and stuff. So this Hugging Face function is actually going to give you back another function. And so say you call this function and you say extractor equals Hugging Face image extractor VIT, this and that, which is a model offered by Hugging Face, comma, CUDA, colon 0. That's going to give you back a function that takes as input a batch at the time and gives you back the features. So for the batch, you're going to have, say, a 32 by 3 by 224 by 224 input, which are essentially 16 different images. And you're going to get back 16 by 1028, 16 by 512, whatever the model is doing. And then you can start storing them in a list, and thereafter you can kind of concatenate them and create your data set. We'll see how to do that. So that's what the first Hugging Face image extractor is doing. Again, you only need to go to Hugging Face models. On the left-hand side, what I forgot to say, on the left-hand side of the web page, you have filters. So if you want to load for a computer vision task, you go to the computer vision section of the whatevers, and you, for example, click image classification, and then that's going to give you back all the models you can load. So you can do, image classification on the top right for computer vision. So you can basically just copy paste the string that you see here and load Google/VIT base path 16 224, whatever. And you can, there's a bunch of models. The repo, the utilities right now are designed for basically image classification only. But you can expand them to leverage other capabilities if you want to build something more intricate in your projects. So if we go to the second functions, the second cell, we have ResNet extractor. And for ResNet, as I said earlier, they are named after their depths, and we're going to be using Torch Vision to load that. You can see that it's also available on Hugging Face, but it's cool to have like a diverse arsenal of tools to use. So here, instead of the string, you just pass it the depth you want to use, and again, the device, and the function that you're going to get as a result works similarly. You go from input batches to output features. Now, for more intricate structures, we have the multimodal extractor. So what the multimodal extractor is doing is, then again, it's from Hugging Face. So you can go to Hugging Face and find multimodal models. So for example, that's the first filter you'll see. And for example, one example is the visual question answering, like a filter where you can load examples from that. Etc. There are other models that are not shown here, which are more like vanilla models that haven't been catered to a specific example. But you know, if you're looking for something particular, like, you can communicate with us as well. And what the multimodal extractor is doing is, that's where you leverage your text inputs. So what you can provide is, like, for each image you have, you can provide various numbers of textual inputs. So I don't know, you can have image and then 3 questions. And then it's gonna go, and for each image and for each one of its texts, it's gonna, like, give you a feature embedding. It's gonna compute an embedding for you. So if you have 3 questions per image, what you're gonna get in the output are 3 different embeddings. So each embedding is going to have an image and a piece of text coupled together, passed through this multimodal encoder, and you're going to get just a feature vector for the pair of them. So remember, as we said, that transformers are universal encoders, and what I meant by that was they encode visual language, visual images. They also work on audio and stuff, and therefore people are also using them to combine in the input both language and images. So you can use the same transformer, have on one side images, on the other side text, and get in the output some, like, representation that incorporates information from both modalities. And so, yeah, that's how this works. So say for a batch, you have a batch that has 16 images, only one text, piece of text per image. You're going to get in the output 16 by the dimension of the output of the model, say 16 by 768. If you have an image and 3 pieces of text for each image, you're gonna get back 16 by 3 by 768. So that's up to you what task you want to design. I've also added some, like in the implementation, the ability to pass only one sequence of texts and have it propagate to all different images. And why I did that is mostly useful for the next block, the multimodal predictor function. If you go to the next code block. So there you'll be able to leverage models like Clip. So what Clip is doing, say it's, you can, for example, in the inputs, you can have whatever images you want, say images of animals. And for the texts, you can have, this is an image of a cat. This is an image of a dog. This is an image of a blah, blah, blah. One sentence for each one of your classes. And then Clip is going to tell you which class is more likely to be present in the image by virtue of like the piece of text that you have defined. So I have an example, like I saw examples of how to define those utilities and to use those utilities. So you'll see an example of us doing that. So in the next cell, I'm just defining a dictionary where I'm storing all the different extractors that have been implemented. So so that it's easy for you guys to just, you know, print models and you'll see what you have access to. And finally, it's probably the function that you are going to use, which is the extract features, where here again, you're just providing the model type, and the model type should be a key of the models dictionary that we just defined in the above cell. So if you want to do feature extraction from images using Hugging Face, model type should be equal to Hugging Face _ image. The model name is thereafter the first argument to the extractor you want to use. So once you define the extractor, you need to remember what the inputs to the extractor are. Again, for most of them, it's just the string from Hugging Face models, but for ResNet, it's going to be its depth. So that's where you pass it here. You pass your data set that you have created earlier when you have loaded your data using the implementation of image dataset that we have here on the notebook. Then it's the extraction batch size. So that's where you may get out of memory errors. If your batch size is too large, it's not going to fit into the GPU, and you're going to get errors from Python. So I've set it to 32. And why I'm doing that is because we are actually not going to train the models here. So this is just a fixture extraction with the pre-trained models. You're not going to be doing any fine-tuning. And what's most expensive when you are running neural nets is during training, because during training, you need to store intermediate values to be able to backpropagate the errors from the top to back to the beginning. And when you are actually storing these values, you are using GPU memory. Whereas when you're just doing feature extraction, for example, without any intention to train, then you can turn off this functionality of storing intermediate values. And it's going to save you a lot of memory. So you can actually increase the batch size much more maybe, but we are dealing with images here. So images are very high dimensional. If you're just dealing with text, for example, you can indeed increase the batch size to a very large number. And finally, the device, again, it's optional here by default. It's going to give you what's available. So if you don't define this and it finds a GPU, then it's going to use the GPU. Otherwise, it's going to use the CPU, but you can manually use the CPU if you so wish to. And what the function is essentially doing is it's creating the model, it's creating the data loader, and then it's looping over the data loader to create the embeddings. And what's important for you is at the output, you're going to get a data set. So this tensor dataset, which I'm calling here, that's a utility provided by PyTorch. So remember, the embeddings are n by the dimension of the embedding. So if you have 60,000 images and the dimension you extract is 768, it's going to be 60,000 by 768. And the labels are going to be 60,000 dimensional, or if you have multiple labels per example, there may be 60,000 by however many labels you have. And when you have tensors that have the same dimension on the left, the first dimension is the same, then you can use the tensor dataset wrapper to create a PyTorch dataset without having to define it yourselves. So this tensor dataset, when you do tensor dataset embeddings labels, so store it in a DS variable and you do DS square bracket 0, it's going to give you back the first embedding and the first label. So that was it with the utilities that we're providing. So let's see how you can use them. Very briefly, I mean, we are sort of running out of time. I don't know how long you guys can stay also. Yeah, do you have another half an hour maybe?
I have to like 1:15.
Okay, I mean, let's go through it quickly. So for the dataset, note what I'm doing first is I'm loading some image from the web. And it's loaded into the variable image. And then I'm defining that my dataset, I want it to have 100 images inside. And for these purposes of these like dummy toy demonstrations, I'm just copy pasting the image 100 times basically to create a list of 100 images. And for the labels here, I guess you have to trust us that this torch empty random int creates labels for you. So you can see what the image is. Again, it's the same that we showed after the flowers in the Torch Vision image manipulation example, the workshop. So what we're doing afterwards is you're going to the split, you're going to use the split dataset function, and you're just going to pass the number of images you have, and it's going to give you back the indices that its split is going to include. So see in the next cell where I'm adding the indices. So indices, these indices, trainings, devins, and testings are all lists of indices. And they essentially like contain the indices from the images that you'll have to use for training, the indices you're going to use for development, and the indices you're going to use for testing. And in the next cell, I'm kind of trying to prove to you that when you concatenate these lists, so when you add two lists in Python, it concatenates them. If you print the length of the set of these indices, so when you pass an iterable through the set function provided to you by Python, it's gonna throw away duplicates. So you can see that my original len was 100, and when I'm doing len of set of ints is still 100. So that means that trainings, devins, and testings contain mutually exclusive, say, indices. So you're not going to be using something that you need to evaluate your internally your approaches. You're not going to have it both in the train and the development indices, and whatever you want to test for the final, like whatever test you have for the final presentation, you won't have access to it until you do the final evaluation, hopefully. So next cell is how you would create only an image data set using images labels and your indices. So these are the three arguments. And then you can see you can access with square brackets. Square bracket 79, that's the final image in the dataset. So remember that the ratios for the splitting are 80%, 10%, and 10%. Since n is 100, that means that for training you have 80 images here, and therefore that goes from 0 to 79. So 79, then square bracket 0 is going to grab the image. Square bracket 1 would grab the label. So because the image is an actual image class, it comes from Python's PILO, which you import from by using PIL, all capitals. If you do .show, it's gonna show you the image in the cell. So I'm showing you that indeed we have the same image still. But let's do something more intricate. So in the next cell, we're gonna take advantage. We're gonna leverage the transformations given to us by Torch Vision to standardize and augment our dataset if we so desire. So you can see that I'm defining and add 2 extra arguments here when I'm calling the image dataset. Firstly, we have the augmentation transform, and that's whatever Torch Vision transformation you wanna use. So for now, like one thing we can use is we can first resize the image to be 284 by 284 if it's square, but what resize is doing is it takes the smallest dimension and maps it to 284, and the other one just gives the aspect ratio for it. And then you do a random crop of the image, and I'm passing this transformation to my dataset, and I'm also saying that I want you to apply the transformation when I'm actually fetching the image. If this argument is false, then it's going to apply the transformation once in the initialization, and it's going to give you the same images back. So for example, see that when I'm fetching 79 2 times, you see I'm getting different crops, and both crops are dimension 150 by 150. And that's because, again, this transformation, the resizing is deterministic, but then I'm using random crop. So it's taking a random crop from the image and giving it back to me. So if you run through the image 2 times, you get 2 different crops of the same image. So that can be useful, I guess, again, as we were saying, for data augmentation during training. Although note that if you're using a pre-trained neural net, it probably has learned that different crops of the same image have relatively similar representations. So you may not get much out of it, but it's something you could experiment with. And if we go to like the next data set that we're defining, you can see that if you disable apply augmentation on fetch and you fetch 79 2 times, you're going to get the same image again, because it applies the transformation once during initialization and then gives you back the same thing. So that doesn't apply, like it's not data augmentation here, but you can still use the transform to standardize the dimensions of your inputs. You may want your images all to be 224 by 224. So you can do that. And that's also less computationally intensive, because each time you want to fetch an image, you don't have to perform the augmentation or the transformation rather. Finally, one more thing is that in Torch Vision, you can have the transformation give you back multiple images as a result. So one example of that is the 5 crop. As we saw in the workshop, the 5 crop is going to take every edge and then the center of the image, and it's going to give it back to you for each image. So preferably when you're doing this, you want to do this once during initialization. So that's a way for you to do augmentation, but not have to compute it over and over again every time you want to fetch the image. And keep in mind that when you're doing this 5 crop, so one image turns into 5. And therefore, when I'm printing the length of the dataset, so the size of the dataset, it goes from 80 times 5, 400. So it's actually increasing the datasets that you're storing in the memory of in your RAM, for example. And the next cell, you can see what the 5 groups look like. So if you go to the original image, the 5 groups are giving you indeed top left corner, top right corner, bottom left corner, bottom right corner, and center. And the next cell, again, from these 5 plots is just to verify that indeed you have applied this transformation and the label also propagates to match the examples. So if you go to the first 5 examples, which are going to be the 5 different crops of the same image, you can see that the label is the same. Next, I'm defining a dataset that also incorporates text. So in that case, I'm defining 2 dummy texts and then multiplying them by n/2. So that's going to create a sentence for each image, even though they are the same. But you have 100 images. You're also going to have 100 pieces of text, and therefore the image dataset is going to interpret that as each individual text matching the corresponding image. So you can see in the like demonstration in the next cell how what you get back from the dataset. So you get 4 outputs this time instead of 2. You get the image itself, as always. You get the label. You get the text that you have provided. And you also get at the output whether this text is the same for all images or whether it's you have pairs. And why that's useful is because you may have a batch size that's equal to the number of images, to the number of texts you have. So say you want to do a 10-way classification and you have your text to be, for each image you want to be, this is a picture of a cat, this is a picture of a dog, this is a picture of blah, blah, blah. So your code won't be able to tell whether the 10 in the texts is because of the batch size or it's because you have 10 texts for each image. So you have another Boolean value which tells you what's the case. And you can see because I created 100 pieces of text, you can see where it's plotting false. That means that you don't have the same text for all images. It's individualized, it's personalized to its image. So it shows you there. It shows you the text that comes with the image, and you also get the label and the image itself. And finally, the last example is where you are indeed creating an image dataset that has only 2 sentences, and they are supposed to match to all the images instead of matching to just the first 2 or whatever. So in that case, you can see in the next cell where I'm printing out what text I'm getting. I'm actually getting a list of texts, and the same text variable is this time true because this text is for all images. And thereafter, yeah, I think we are going to examples of how you can perform feature extraction by using the dataset. So you go to models again, I'm printing the models, and you can see what models you have access to. It's a whole separate section. So if you scroll up and you, oh yeah, that's it. Oh yeah. So I have examples of different scenarios that you might want to use. First is simple image processing with Tort Vision. So let's see a couple and then let's start discussing your projects. Or since you have to go in like 5 minutes, do you want to discuss anything right now? Did you go over the links? Do you have any ideas what you might want to do?
I thought of like one idea, but I don't know if it's advanced enough for like the scope of our project. I was just thinking of like image classification of kind of random like artwork, like detecting like what kind of style art it is based off of like image processing, but I don't know what are the requirements for the project. So
I think we were talking, and I mean, people have different levels of like experience with machine learning and stuff. So whatever level of project you want to do is fine. However, what I would say is that you could put your effort into actually collecting the data, for example. So you may have to scrap the internet to find the data you want to find. And in that case, that's actually a valuable contribution because half the story is the data. Like pretty much nowadays, like people just need to find the data that they apply to an already existing architecture. They don't have to deal with like defining their own stuff. So if you find your own data, then that's perfectly fine. And if you have no prior experience with machine learning, then I guess maybe going and tweaking some of the tools that we are providing, maybe warranted instead of just feature extraction and then SQL classification. But if you do the data collection, then I guess it's fine. So do you actually have a data set in mind, or do you know where you might download data from, for example?
Haven't looked for that yet.
Okay, yeah. So bear in mind that whatever you want to do, you also need to have access
Yeah.
to some data. So you could be looking for, like in GitHub, if you go on GitHub and you start searching, people have compiled lists of projects as well beyond the ones that we share, and perhaps lists of image data sets that you may want to look at. Or you can say, also find like an existing data set and try the clip method that I mentioned earlier, where you say, this image is in the style of this image is in the style of that, and try to see if that works, how you can perhaps tweak it to make it work, stuff like this. But first, like, yeah, the first thing that you should focus on is finding data.
What are you guys' names? Jenny.
Oh, I'm Anushka.
And Adam.
So with your artwork project, I guess you could probably like scrape some like sale website. They probably have a lot of data that's like already organized, so you would have to label with that instead of like manually going and labeling those like randomly collecting from Google and then labeling them yourselves. You'll probably just like scrape. But with that, you'd have to be careful about like, so you need a lot of images, right? It's not like you'll be able to do it with like 1,000 images. It'll be like probably like hundreds of thousands of images will be necessary for you to like get a nice enough accuracy. So just be careful with the scraping of that.
And be careful with what the copyrights of the images are.
Oh yeah,
Exactly.
So for your use or whatever, or for the purpose of this project, if you don't open source anything, maybe it's fine. But if you want to release, say, a paper, or you want to open source a GitHub repo that has the data or whatever, then you need to actually have the permissions for the images. And it's going to be for research purposes. We're not building any.
commercial.
Yeah. So, yeah.
There is actually a data set.
There is.
Yeah.
Yeah, so first would be how to collect your data. The second would be like going onto archive and then finding papers that have already done what you're trying to do, and then think about how you can improve, or even if you're able to replicate the results. I think that's also like really good accomplishment, given that we just began this right now.
What's your level of experience with machine learning?
Close to 0.
Just a 0, okay.
Yeah,
There
that's-
are, you can also do style transfer, where you take an image and kind of extract the style from, say, a painting from Monet or whatever, and then you take an actual photograph and try to make it into the style of the painting. And you can, there are pre-trained models that do that, but definitely not ones that fit my the templates that we have included here. So if you are not experienced, maybe don't go that route. But if you want to start working now and leave your room next time for the presentation in a month, then it's fine. Maybe you can also look at diffusion models. Maybe
That was where I went, but then after like that would be quite expensive. Like you need that many credits to like get that much data.
Yeah.
So how do you guys want to do that? Are you comfortable So assuming that the four of you are the only people who are doing projects together. Did
Uh,
anyone reach out to you?
yeah, I met with some students yesterday
Oh,
who have a conflict with like this time frame.
so let's say like 3 people, 3 or 4 people per group.
Yeah, it's also good to if you guys can collaborate. So if
Yeah,
because you
just
can
like open
coordinate.
up the Slack channel to conversations, so you know what kind of people, and then elaborate and discuss that.
So 3 to 4.
Yeah, 3 to 4.
And
per
I mean, you can
group.
go for two also if you are comfortable with that. So like maybe 2, 3 or 4 that you can make your teams content.
Then also let your like group mates know like how much time you can commit to this. So if it's like 2% per group, then it's gonna be a lot of free time.
okay, let's discuss for the project instead of going over the code. The code I think should be fairly simple for you guys to digest now because I'm just here. I have some very dumb examples of creating a transformation, then the image dataset with the dummy images and labels, and then just doing some feature extraction to see how it works. So depending on your application, so you can go over that by yourselves. Oh, I thought we had a participant.
Sorry.
You have joined the Zoom. I just saw. that.
Sorry to giving that expectations.
Yeah, I
Did you
guess-
guys go through the first link that I sent?